Avogadro's law. So far, all these things we've been talking about, the amount of gas hasn't changed. But what if the amount of gas does change? Where have we heard this name before, Avogadro? Avogadro's number. And what was Avogadro's number? 6.022 times 10 to the 23rd, and that was the number of things in a mole, right? Avogadro also worked with gases, and actually it was his work with gases that led to the understanding of what that number is that bears his name was and how it's useful and what a mole was. And so when we look at Avogadro's law, we change the amount of gas, and we're measuring the gas in terms of moles, not by mass. Moles relate to number of particles. So we measure the number of moles of gas, and we find that there's a linear relationship with volume. If you double the number of moles, let's see, like from here to here, then you double the volume. 15 up to about 30. It's a little hard to see in that graph, but it's true. The volume of a gas increases linearly with the number of moles. So Amadeo Avogadro, how's that for a name, lived a long time ago. He was born at the same time our country was, 1776. It's a long time ago. And he studied gases, and he found this relationship. When we look at Avogadro's law relating volume and moles, we are assuming that the temperature is constant and that the pressure is constant. And so we state Avogadro's law like this: the volume of a gas and the amount of the gas in moles are directly proportional. And what I left out of the slides was writing it out in V1, N1 type form. So here, I'll write it in here for you. V1 over N1 is equal to V2 over N2. It's a lot like the volume temperature relationship. When one goes up, the other goes up. When one goes down, the other goes down. So that is Avogadro's law. Let's do a problem with it. Oh, but first let's look at a picture of a cute little boy with a balloon. Random, huh? This relationship between amount of gas and volume should intuitively make sense to us. Because like with this little guy, you take a balloon and it's got some air in it and it has a certain size. If you blow more air into the balloon, does it get bigger or smaller? It gets bigger, of course, right? We all have experienced that. You put more in, the volume increases. Here we have a problem. A 4.8 liter sample of helium gas contains 0.22 moles of helium. How many additional moles of helium must be added to the sample to obtain a volume of 6.4 liters? Okay, another one of those whole bunch of words with some numbers in there. Let's make a table. Tables are good. One and two. First number, 4.8 liters. All it says is a 4.8 liter sample. Doesn't tell us the name of the quantity. But liter is a unit of what? Volume. So this is the volume of the gas. We tell that by the unit. So that's volume. Contains 0.22 moles, so let's write that down, 0.22 moles. This is our new variable. Remember what the letter was? It's a lowercase n. N stands for number of moles. Number of moles. So 0.22 moles of helium. And then we go on to the next number, 6.4 liters. Okay, so that must go in the volume column. And we're out of numbers. So we'll finish off our table. I'm going to erase these lines that I drew that were too long. So what can we find from our little table here? What should we write in this box? N2, right? That doesn't look like an N. N2. What's the question asking? How many additional moles? What does N2 tell us? The total number of moles at the end, right? In this balloon, when it is big 6.4 balloon, it doesn't say balloon. We'll just call it a balloon. In this balloon, when it is 6.4 liters in size, N2 is the number of moles that are in there. But the question says, when it was smaller, it had 0.22 moles, and now how many moles do you have to add? It's kind of a little twist in there, isn't it? So you got to read these carefully. So if we know how much there is at the end, and we know how much we started with, how can we figure out how much we need to add? Just subtract, okay? So we're going to solve for N2 and recognize that that's not our final answer. That's our total number of moles. And from that, we're going to subtract what we started with to answer the question that's being asked. So that's a little tricky. So our equation is going to be Avogadro's law, because we've got volume and N, V and N. And so the equation is V1 over N1 equals V2 over N2. And we are solving for N2. We've got fractions. Cross multiply. Get rid of the fractions. What's this going to be then? What's on the left of the equals? V1 times N2, and that is equal to what? V2 times N1. If you wrote N1 times V2, same thing. So we cross multiplied. I'm just going to highlight this in yellow again to help us remember what we're looking for. What do we do now to get N2 by itself? Divide by V1. That makes V1 over V1 is 1, cancels out. We did it to one side, we have to do it to the other side. Now we have our equation. N2 equals, bless you, V2 N1 over V1. So V2 is 6.4 liters. N1 is 0.22 moles. V1 is 4.8 liters. And we check the units, and they cancel out, so that makes us happy. So N2 equals, calculator, 6.4 times 0.22 divided by 4.8 equals 0.29333, repeating forever. How many sig figs should we have? 2. All of our numbers had 2. And you'll find that in the problems that we set up for you, that's a lot of times that's the case. Nobody's trying to trick you with sig figs. It's going to be generally 3 or 4 sig figs, sometimes 2. So here, 0.293, I'm going to round off to 0.29 moles. But that's not our final answer. That's the final number of moles, but remember, we were trying to figure out how many moles we had to add. So we're going to take 0.29, which is what we end up with, and we're going to subtract what we started with, and we are going to come up with 0.07 moles. So to make that sample go from 4.8 liters to 6.4 liters, we would have to add another 0.07 moles of helium. Any questions?